Okay, our next topic is gravitation and the orbit problem. Now, we have thus far focused on the gravitational force that a mass experiences on the surface of the Earth, but in fact, gravity is universal, and um, you have a force of gravity between any two masses in the universe, an attractive force. So here we have two masses, say a bigger one and a smaller one, and there's a force of gravity between them. Big M is attracted by small m, and small m is attracted by big M. And the question is, how does the magnitude of those two forces compare? Are they equal? Is one bigger than the other? Think about that for a moment. Well, hopefully you agreed that the forces have to be the same, because the amount of force depends on both the mass being pulled and the mass that's doing the pulling. So it depends on the product of the two masses. And consequently, whether it be big M, little m, or little m, big M, doesn't matter the order, the magnitude of the force will be the same. Another way to argue is that these are an action-reaction pair, and that consequently the forces have to be equal and opposite. Now, in addition to varying directly with the product of the two masses, it turns out that the force varies inversely with the square of the separation distance. And then there's an experimental constant of proportionality, capital G. It's called the universal gravitational constant, and it's very small. It's 6.67 times 10 to the minus 11. Now, more on what that means shortly, very shortly, in fact, because we'll do this example. So here we have two 1 kilogram masses held about a meter apart. We'll find the force of gravity between them. Now, first of all, we know that gravity is attractive, so these two masses are pulled towards each other, and the magnitude of the gravitational force is given by this expression. Now we'll put the units in once here. So the units of the gravitational constant are Newton meters squared per kilogram squared. Then the two masses, well, they're each a kilogram, aren't they? And then the distance r is separated by a meter. Now notice dimensionally that the kilogram and kilogram cancels that, kilogram squared, and then the meter squared is canceled out, so you're left with an answer in newtons, which is good because it's a force. And then we see the answer is 6.67 times 10 to the minus 11 newtons. So the constant, this universal gravity constant, is exactly the force between two 1 kilogram masses separated by a meter. And if you increase the mass, then you'll have a larger number in here, and the force will, of course, be different from this. But this, if you like, is sort of a scale factor. It tells us how big the force is in this situation, and that if we change in the masses of the distance, then we will just scale this answer up. It also shows us that gravitational forces between two masses, anyway, tend to be very, very small. Now let's look at what it means to be an inverse square law. Let's imagine that we have two masses separated by distance d, and the force is F. Now, what happens to the force if we double the distance? So let's take this mass and we'll pull it way down to here. Okay, so now, is the force the same, or is it smaller, or is it bigger? Well, because the force varies inversely with distance, we notice that the masses aren't changing here. What's changing is the distance instead of d. So this force, the original one, for the purposes of comparison, is gmm over d squared. So doubling the distance, we've got a factor 2d that needs to be squared. That's actually going to give you a factor of 4 in the denominator. So the force, if this was F, this force is now 1/4 as much, F over 4. So these arrows should be a lot shorter. Now, to make sure we understand that, let's see what happens if we actually triple the distance. Well, now, in the denominator, we'll have gmm over 3 times the separation distance. After you square the 3, there will be a factor of 9 in the denominator, so the force will be 1/9. So if we double, triple the distance, then this force is now F over 9. Now, to check for understanding, If we quadruple the distance, we now expect it'll be 1 over 4 squared, or 1 over 16th. Now, if we come back to that original problem here where we had m and m, what happens if we double one of the masses? Well, in that case, the distance, we're back to just a separation distance d, we see that we're going to get about twice the amount, well, exactly, sorry, twice the force we had by doubling one of the masses, and so on and so on. So this is an exercise in proportional reasoning. Okay? And one of the important conclusions to that exercise is that doubling the distance actually gives us 1/4 the force, and so on. Tripling the distance is 1/9, and so on and so on. So we saw that gravitational forces are very small. There's one way that they can become significant. That's if you have a really, really big mass, like a planetary object. So let's look at the Earth. Here's the Earth, and let's pretend we knew its mass and we knew its radius. And then let's find the force on a 50-kilogram student on the surface of the Earth. Now, for the distance r, it's a center-to-center distance. And so even if we're on the surface of the Earth, this distance is not 0, because we have to measure how far it is from the center of the 50-kilogram person to the center of the Earth. Well, that's basically going to be the Earth radius, because this little distance, from ground level up to the center of mass of the person is negligible, as is, any small variation over the surface of the Earth in terms of that distance, because the Earth is not a perfect sphere. It's actually a little bit further from the equator to the center of the Earth than it is from the pole, because the Earth is a little bit squashed like that. Okay, so let's find that force. Now, I'll drop the units this time because we did it last time. So it'll be g(m)m) over the distance squared. 6.67 times 10 to the power -11. So we'll substitute in the given value for the mass of the Earth, 5.98 times 10 to the power 24. The mass of the person. We divide by the given radius of the Earth, and all of these are incorrect units. These are in kilograms, and this is in meters. And we work that out, and we find out it's about 490 newtons. And there's a bunch of decimal places there that I'm not writing out, but this, in a way, shouldn't really be a surprise, because if you found the force of gravity the other way, which would just be force of gravity is mg, then multiplying 50 by 9.8, you get exactly 490 newtons. So this is actually telling us something quite interesting. It's telling us another way, or another way of finding out what the gravitational field is on the surface of the Earth. Because you see, up until now, we knew that gravitational field strength was a ratio of weight to mass in newtons per kilogram. Right? And on the surface of the Earth, we knew it was 9.8 newtons per every kilogram of matter. Another way to find the gravitational field is to do a free fall experiment, because in free fall, the only force is the gravitational force, and that will be the net force, and therefore equal to ma. So the acceleration is just the same as the gravitational field is the same as the free fall acceleration. And so on the Earth, it's 9.8 meters per second squared, because the gravitational field is 9.8 newtons per kilogram. On the Moon, the free fall acceleration is only about 1.6 meters per second squared. But neither of those determinations of the gravitational field strength G have anything to do with the planet. Well, now, finally, we can relate it to the planet. Comparing universal gravity, the force of attraction between the Earth and a mass on its surface, and this sort of simple experimental version, I suppose, of the gravitational field, we can see that this here and this here have to be the same. So that tells us that we can find the gravitational field strength by multiplying the universal gravity constant, the mass of the Earth, and then the mass of the planet, and then divide by how far we are away from the center of the planet squared. So that's how you can find the gravitational field. All you have to do is find the mass of the planet and how far you are away from it. But of course, finding planetary masses wouldn't be easy. I mean, what sort of scale would you use for that? So, in fact, one of the most useful, one of the most, I suppose, useful applications of this is to actually find the mass of, say, the Earth, because we know what the free fall acceleration is, and we know what the radius of the Earth is from other measurements. So we can take this equation and we can turn it around and solve for the mass, big M. So we cross multiply the r squared up, then we divide the universal gravity constant down. So that little bit of cross multiplication gives us an expression for the planetary mass. So here we had 9.80 meters per second squared, or newtons per kilogram. The R was, well, we had that before, 6.38 times 10 to the 6 meters, and then that's all squared. And then we had 6.67 times 10 to the minus 11 power Newton meters squared per kilogram squared. Okay, so I suppose a thought about units here. So we've got meters squared and meters squared. This one will cancel, so this one will survive. And then we've got a Newton, and a Newton, of course, is a kilogram meter per second squared. So if I put that in, kilogram meter per second squared, then I see, okay, the second squared will cancel, the remaining meter will cancel, and one of the kilograms will cancel, and hurrah, we've come up with kilogram units. That's good, because don't forget, we're solving for big M, the mass of the Earth. It should be in kilograms. Now, if we crunch these numbers through, no surprise, we get a value of the mass of the Earth of 5.98 times 10 to the power 24. Of course, this is where the number came from. Okay, so this then is the universal law of gravity and its use in calculating the gravitational field strength of a planet, or potentially the mass of the planet. Now, why are we talking about this in the middle of a unit on circular motion? Because the orbit problem is an example of circular motion. So little m, this could be like the Earth orbiting the Sun, or it could be a satellite orbiting the Earth, or the Moon orbiting the Earth. But this little m going around in a circle must have, first of all, it's accelerating, because anything going in a circle is accelerating, and therefore there must be a force. Now, the direction of the acceleration is inwards, so the direction of the force must be inwards. So what real force is inwards on little m? Well, it's the force of gravity. So if we apply Newton's second law, we know the net force is always equal to ma. What is the net force in this case? Well, it's the force of gravity. Now, we're not quite done here yet, because of course we know that the acceleration when you're going in a circle is v squared over r. So if we look at this relationship, we see that, so you've got the mass little m, oh, that's going to cancel out. You've got the mass big M, that's the planet mass. So if you know how far you are away, you know the planet mass, you can find out how quickly you're orbiting. You can calculate the orbit speed. So let's just write that again. Here's the force equation for an orbit. It's the inwards force is the force of universal gravity. So we've got a big M and a little m, and it's little m that's going around in the circle. So be careful to put little m times a. And there's the acceleration when you're going in a circle. So little m cancels, one of the r's cancels, and we find out an expression for the orbit speed, v. Now this is v squared, so we have to take a square root. It depends on the mass of the planet and how far you are away from its center. So let's see. So we got a satellite orbiting above the Earth's surface, and that means that big M is, of course, the mass of the Earth. So we look on our formula on our data page and see what the mass of the Earth is, or we just turn back to the previous page. Then we need to know what's the distance from the center of the Earth to the center of the satellite. Well, note that we were told that this is 20,000 kilometers above. So we're 20,000 kilometers above the surface of the Earth, but of course this is not the radius of the circle. This is not the distance between the two masses. So we actually need to take this 20,000, which is measured above the surface of the Earth, from here to here, and then we need to add the 6,380 kilometers of planet radius. That's the radius of the circle. So that value then is 20,000 plus 6,380 kilometers. That's in kilometer units. And so that is 26,380 kilometers, or 2.638 times 10 to the power 7 meters. So when we put that in there, and don't forget to take the square root, when you work this out, you find that the orbit speed is 3890 meters per second. It's about 3 kilometers per second when you're 20,000 kilometers above the surface of the Earth. Now, that orbit speed is an interesting result, and it's worth writing down. It depends on big M. Interestingly enough, it doesn't depend on little m. So a speck of dust is going at the same speed as a space shuttle at that elevation if they're in orbit. Now, another interesting thing about being in orbit is that you're in free fall, because if we find the inwards acceleration, which we know is v squared over r, and substitute the expression that we just found for orbit speed, so you've got to square this and then divide by r. So squaring gets rid of the square root. So there's v squared, and then you divide by r. Well, that's of course of gm then over r squared. I was getting ahead of myself there. And that is of course exactly the value that we had for the gravitational field strength. It's the same. So that tells us that our acceleration is the same as the gravitational field strength, but that's the condition for free fall. So an object in orbit is in free fall. It's always falling towards the surface of the Earth, or the planet, I suppose, but never getting there. And here is Newton's thought experiment that led to that realization. He imagined being on top of a mountain and firing a projectile. Now we know that that projectile will fall to ground, say following a parabolic trajectory, which I've kind of sketched roughly here. But of course, Newton said, all right, well, what happens if we really have a very powerful cannon and we fire it off? You know, he realized that that projectile would arc to ground, but of course, the Earth being curved would sort of fall away or curve away so that the cannonball would actually travel farther before it reached the ground. Like if the Earth was flat, it would hit here, but the Earth isn't flat, so that the cannonball actually travels further. And then he reasoned, Newton did, that, well, there's got to be a speed whereby if you shoot it fast enough, yes, it's going to be attracted by gravity towards the center of the Earth. And therefore, it's going to be pulled downwards and it's going to deflect downwards. It's not going to go straight, it's going to deflect downwards. But the rate at which it's deflecting downwards due to gravity is exactly the same as the rate at which the Earth is curving away because of the fact that the Earth is round. This, of course, is an orbit. So if the ball was going at just the right speed, then it would fall to the Earth at the same rate the Earth curved away from underneath it. And the ball would then be in orbit. So we know that this ball, this cannonball, is in free fall once it's projected. So that means this one's in free fall. As it goes around and around and around the Earth, you're constantly falling, but you're never reaching the Earth, which agrees with what we just derived here, that your acceleration when you're in orbit is the free fall acceleration. So that's very interesting. An object in orbit is in continuous free fall. So you're always falling towards the Earth, but you're never getting there. So, you imagine being up in orbit for, like a day or something like that. The most any of us have ever experienced free fall is usually for a second or two, maybe off the 10-meter platform at the pool, and the experience is something like and then you're in the water. Well, imagine feeling like that, experiencing the physiological sensation of free fall for days. You know, you're always falling all the time, but you're never landing. Now, this, of course, explains why astronauts seem to float in the space shuttle. They're not really floating, they're experiencing a significant force of gravity up there. But the passengers in the ship are both falling at the same rate, and consequently, the ship isn't there to support them. So they experience what we call apparent weightlessness. There's no normal support force from the floor because the floor is falling away. All right, so this is an introduction then to both universal gravity and to the orbit problem that we'll pursue a little bit more in class. We'll do a couple of examples, and then we'll look at what we call combo questions again. That's our video for today.